Okay, and we spent a lot of time in this last chapter talking about thermodynamics, right? Whether or not a reaction occurred spontaneously or non-spontaneously, which is really just saying it would occur spontaneously in the reverse direction, okay? Spent a lot of time talking about those thermodynamic variables, how we can predict that sort of thing. Now we're going to switch gears and we're going to start talking instead about, please work, there we go, talking about reaction kinetics, okay? So the speed of a reaction. And we talked about how these two concepts, although they seem like they should be one and the same, like it seems like logical that a reaction that happens spontaneously also happens quickly. They're actually completely divorced concepts, right? We talk about thermodynamics, we talk about kinetics, they are not one and the same thing. So what we talked about last time was thermodynamics, whether or not a reaction happens spontaneously. And now we're going to investigate the speed of a reaction, the kinetics of a reaction. We looked at this diagram here where we're plotting free energy versus reaction progress, okay? And we said the thermodynamics of this reaction was really just looking at the endpoints, looking at the difference between the energy of my reactants and the energy of my products, right? My delta G. But again, thermodynamics only concerned with the endpoints. Everything that happens in the middle here, this is the kinetics of a reaction. So what the heck do I mean by that? All right, so how we think about reactions is they have to overcome this energy barrier here, right? This little hump that we have in the middle. Our reaction, in order to get from reactants over here to products, it's got to make this jump over this barrier, okay? This barrier here we call the activation energy. Let me actually make a clean plot here. So again, we had free energy plotted against reaction progress. We get this little hump looking thing. Okay. Again, the difference in energy between my reactants and products, this gap here is the delta G of my reaction, right? Just the straight up difference in energy between the reactants and products. This little hump here is what's called the activation energy. All right, and again, in order for a chemical reaction to go from the reactant side over here to the product side, over here, it's got to jump that activation energy, right? It's got to overcome this energy barrier there. Okay, so let's take a look at two of these sort of graphs next to each other. All right, and for both of these, I'm going to sort of have them starting and ending at the same place. So there's no difference in the thermodynamics of these two reactions. But for this one on the left, I have this really tiny activation energy barrier compared to this one on the right where I have this very large activation energy barrier. All right, so on the left here, so I guess if I'm being good, I'm going to label my axes free energy, reaction progress. right? The difference here is that this terribly drawn one that I have to redo or it's going to drive me nuts. Okay, this has a very small activation energy. Whereas the one on the right has a large activation energy. All right, because again, activation energy is the size of this hump right here that my reactants have to jump over in order to become products. So again, both of these reactions, my reactant and my product, same energy level, right? So the thermodynamics of these two reactions are identical. The difference is the activation energy barrier for the one on the left is much smaller than the one on the right. A small activation energy corresponds to a fast reaction, whereas a large activation energy corresponds to a slow reaction. So the world is full of reactions that technically occur spontaneously. Okay, so for example, the graphite in your pencil will spontaneously convert into diamonds. Fantastic, right? But we're not all going out and investing in a bunch of pencils and hoping to then turn it in to the jewelers the next day, because this reaction occurs over a span of billions of years, right? So despite being a spontaneous reaction, something that from the universe's standpoint happens favorably, it's a reaction that occurs over this like ridiculously long period of time. Right? So spontaneous does not necessarily equal the same thing as fast. They're two different concepts. And that's what we're exploring in this chapter, is the idea of reaction speed. Okay? Fast versus slow reactions. All right, so first of all, how do we go about measuring reaction rates? So again, kinetics, that's the focus of this chapter. And really now we're interested in the speed of a reaction. When we talk about speed, we're really talking about what we call in fancy chemistry terms, the rate of the reaction. All right, and we actually deal with speeds all the time. Okay, so for example, when we're driving, how do we measure how fast our car is going? Miles per hour, right? That is the rate that our car is traveling. Okay, so when we're talking about the speed of a car, again, we measure that in miles per hour, which is the change in distance divided by the change in time. All right, so when you're driving down the highway at 60 miles an hour, that means that you are moving at a rate of 60 miles per hour, right? Divided by time. Rate of reactions all right, we're also dividing by change in time, but with reactions, we're not actually moving any physical distance. So we're talking about a change in concentration divided by the change in time. Right? How the concentration of our reaction mixture is changing over time. All right, so let's look at a specific reaction here. Hydrogen gas reacts with iodine. Whoa. To produce 2HI. Okay, so when we're measuring our reaction rate, what's going to happen to the concentration of reactants over time? Right, I mix in hydrogen and iodine, and then I start the clock. What's going to happen to the concentration of those reactants over time? Is it going to increase or decrease? Decrease, right, because reactants get consumed. And what's going to happen to the concentration of my product over time? It's going to increase, right? So for sort of just basic idea here, we have reactants decrease concentration over time, and products increase concentration over time. Okay? When we're measuring our rate of our reaction, importantly, reaction rates are always measured as positive values. Okay? So I'm going to construct this expression for the rate of this reaction, and I'm going to keep in mind the fact that reaction rates are always positive. So if I wanted to measure the rate of this reaction, I can measure the change in the concentration of hydrogen gas over time. Okay? But I'm going to have to keep in mind that reactants are always decreasing, and I want this positive value for my rate. So if I'm measuring a reactant, I have to throw a negative sign out front there, right? Because the change in concentration will be negative, so I have to multiply that by -1 to get a positive value. Okay? So reaction rates are always positive, and I'm going to get the same value regardless of what I'm measuring. So I could measure the change in concentration of the hydrogen gas. That would be one way to get the rate. All right? But hydrogen gas might be a little bit of a pain in the butt to measure. For example, iodine's got this bright purple color associated with it. I can take advantage of that and use that to measure the change in iodine concentration instead. And that would be the exact same. Change in the concentration of I2 over time. Iodine is also a reactant. So what am I going to have to do to this expression to finish it off? Minus sign. Right? So it wouldn't matter whether I measured hydrogen gas or iodine, I would get the same value for my rate of my reaction. Right? Iodine and hydrogen are going to be consumed at the same rate in this reaction here. Okay? Or maybe it would be easier to measure the concentration of product, concentration of HI. Since my product is increasing, I don't have to put the negative sign. Okay? But I do have to be aware of my stoichiometric coefficient out front there. For every 1 hydrogen gas and 1 iodine that's consumed, I actually get 2 HIs. And again, one important feature of our reaction rate is that we have to get the same value regardless of what we're measuring. So I'm going to have to divide by that stoichiometric coefficient. So if this reaction is occurring, regardless of which one of these components I measure, as long as I use these expressions here, I'd get the same value for my reaction rate. Okay? And again, my 2, that's my stoichiometric coefficient, appears in my rate expression because I'm going to divide that concentration by 2. All right, so step 1 is how to build our reaction rate expression. So let's get a new balanced chemical equation. All right, so if I'm gonna carry out this reaction and I'm gonna measure the rate of my reaction. All right, let's define our rate in terms of the nitrogen gas concentration. That would be the change in nitrogen over the change in time. But again, since nitrogen's a reactant, I'm going to have to put a negative sign, right? That change value, this value up top here, because nitrogen's a reactant, that will decrease. That will be a negative number. So I'm going to multiply that by this minus sign so that my reaction rate's always positive. Remember, reaction rates always have to be a positive value. That's why we multiply our reactants by -1. Put a negative sign there. All right, so take a minute and give me the reaction rate in terms of hydrogen gas as well as ammonia. Give me those expressions based on our balanced chemical equation. All right, so if I'm going to measure hydrogen, that's also a reactant, so I'm going to have to put a negative sign out front, as well as I have this stoichiometric coefficient. So I'm going to divide my change in concentration by 3 in order to account for that. Right, so in terms of my hydrogen concentration, it would be -1/3 times the change in hydrogen divided by the change in time. All right, and then if I'm going to do my ammonia concentration, ammonia is a product, so that's going to be increasing, so I don't have to multiply it by the -1, but I do still have to account for the stoichiometric coefficient, so this would be 1/2 times the change in ammonia over time. Okay, so that's how I could get my rate expression defined in terms of each reactant and product, right? Again, reactants, we need to make sure to include the negative sign out front. And we always have to divide by that stoichiometric coefficient. That's how we construct our expressions for our reaction rate. Cool? All right, so step one, given a balanced chemical equation, can you give me the rate expression in terms of each product and reactant? All right, cool. So let's take a look. Now let's say that I did measure these reactant concentrations and product concentrations over time in my reaction. For this reaction right here, what I would see would be something like this. I'm going to do nitrogen in blue and ammonia in green here. All right, so we're going to make a plot. On the x-axis, we're going to have time, so how concentration changes over time. On the y-axis, we'll have concentration. All right. So I'm going to start out, I'm going to use, whoops, I lied. I'm going to use blue for my nitrogen gas concentration and green for my product, my ammonia concentration. I'm going to start out with a bunch of nitrogen, and what's going to happen over time to the concentration, increase or decrease? It's going to decrease because it's a reactant, right? So I'm going to see that this goes down. That was terrible. And then what's going to happen to my concentration of ammonia? It's going to increase over time. Okay? Now, we spent a whole bunch of time last chapter talking about this region over here where everything flatlines and is no longer changing. What do we call that region? Equilibrium, right? When everything's reached this steady state, no longer changing in terms of concentration. Now we're kind of more interested in the beginning bit over here, okay? Because we're interested in the rate of this reaction. Okay? And in terms of the rate of this reaction, that's the change in concentration over the change in time. What do we call that from a graphical standpoint? Rise over run. The slope of those curves, right? So the slope of these curves corresponds to the rate of these reactions. Okay, right? Change in concentration, that's what's on my y-axis, divided by the change in time, what's on my x-axis, rise over run. So my rate of my reaction is the slope of these curves. So now everybody maybe got a little bit of a flash of danger in terms of like how calculus is very intimately related in terms of our slope here, right? In terms of our kinetics of our reaction. But this is not a calculus course. All right, so you can see how it's very intimately tied in there, but we're not going to be doing any sort of derivatives or any of that business here. We could, it'd be fun, but that's not the name of the game in this class. All right, what's really important to see from our curves here is how my reaction rate actually changes throughout the course of my reaction. Right? What happens at the very beginning of my reaction to the slope? Is it really sharp or is it flat? Right, so reactions, when they start out really, really fast. But then over time, they start to flatline. Reactions get slower and slower and slower as reactions occur, right? So my reaction rate is not constant. My reaction rate is changing over time. Again, the rate is the slope of this curve. And we can just note from our curves here, our reaction rate decreases over time. Okay? All right, so why do rates of reactions decrease over time? So, turns out that the rate of a reaction is proportional to the concentration of your reactant. Okay? So we're going to look at a really, really simple reaction here, where we just have some reactant A being converted into product. Okay? And again, that rate is dependent on the concentration of that reactant A. Right? So why do reactions slow down over time? Because reactants get consumed, right? So over time, this concentration's decreasing. So my rate of my reaction will decrease as time progresses. Okay? It's proportional to the concentration times some constant, K, what we call, because we're super creative, the rate constant. Okay? But it's proportional to the concentration raised to some power n. And this is kind of going to be our focus for the rest of the class here. This is what's called the order of the reaction. All right, and for our purposes, n is always going to have one of three values. Our reaction order could be 0, 1, or 2. Okay? And a big goal of what we're going to have is finding out what the order of a reaction is. So, one very important thing to understand about kinetics is just by looking at a chemical equation, you can't figure out what the kinetics of a reaction is going to be. You got to actually get in there, do some measurements, collect some data. All right, so we're going to be analyzing reaction data in order to figure out what the rate of a given, or rather, what the order of a given reaction is. All right. Again, our goal is going to be to find n here. That's what we're building up to. All right, n is always going to have one of three values: 0, 1, or 2. So n equals 0. This is what we call a zeroth order reaction. Okay? So let's just think real quick. Let's take this rate expression. And I'm going to have some constant K times the concentration of my reactant to the 0th power. What happens when I raise something to the power of 0? Becomes 1, right? So this simplifies to just my rate equals that rate constant. So for a 0th order reaction, these are reactions that are independent of the concentration of reactant. Reactant, sorry. If we go back to our sample reaction here, is this a 0th order reaction? No, how do we know it's not? Because it's changing, right? If it wasn't, it would be independent. It would be a constant slope. So a 0th order reaction would have these linear sort of lines, right? Constant slopes associated with them. So a linear change in concentration of reactant or concentration of product. They certainly do exist, linear zeroth order reactions. They typically involve things like solids, something that don't have like a variable concentration associated with them. All right, if n equals 1, we call that a first order reaction. All right, and if we plug that value of 1 into our rate expression here, raise something to the power of 1, that's just itself. Okay, so in a first order reaction, if my concentration of A is doubled, what's going to happen to the rate of my reaction? It's also doubled, right? This is what we would call directly proportional. If I cut my concentration in half, my rate's going to be cut in half. If I triple my concentration, my rate is going to be tripled, right? They're directly proportional to one another. All right, and then lastly, again, for our purposes, n only has these 3 values. If n equals 2, what do we think we call that? A second order reaction. Yeah, we're super creative here. That means that my rate is equal to K times the concentration of A squared. So that means if my concentration of A is doubled, my rate, what's going to happen to the rate of this reaction if I double my concentration of A, multiply it by 2? Quadruple, it's going to be multiplied by 4, right? Rate is 2 squared, right? Concentration of A is doubled. My rate is then 2 squared or quadrupled. Because again, it's dependent on the concentration of A squared. All right, so again, given a chemical equation, you really don't know anything about the rate of the reaction. You need way more information than that. So first thing we're going to do is we're going to collect some data, and we're going to interpret that data to determine the rate of a reaction. All right, so I did this experiment here. All right, where I had my A being converted to product. All right, and how these sort of experiments work is we're going to carry out this reaction. At different concentrations of A. And measure the initial rate of that reaction. So we're going to measure the slope at the very beginning, those very first few time points. And then we're going to carry out the reaction again, but we're going to change the concentration of A. We're going to increase it a little bit. Measure the rate at the very beginning. Change the concentration of A again. Measure the rate at the very beginning. Okay? So that's what this data here is, the initial rate of these reactions carried out at different concentrations of A. All right? Now, I realize right now that I gave away the punchline at the very top. Just get rid of that. All right? But if we look at this rate data here, what do we notice about these rate values? They're all the same, right? So that would be a 0th order reaction. It doesn't matter what the concentration is. We get the same rate value. All right? But we need to be able to determine this, kind of not just by looking at it. So what we're going to do is we're going to pick 2 data points, any 2 data points. I'm going to pick this one and this one, column 1 and 2. Okay? And again, our goal is to determine this value right here, the order of this reaction. All right, and we need 2 data points to do this, at least 2. Okay? And that's because what we're going to do is our strategy is going to be to take the ratio of 2 of these points here. So we need 2 data points, and we're going to take the ratio. We're going to stack one on the other, and I'll show why this is important here in a second. So again, our goal is to determine our reaction order. And our strategy is going to be to take the ratio of 2 data points. All right, so that means I'm going to have the rate of one of these data points divided by the rate of the second data point. And again, that's equal to this expression, K times the concentration of A at that first data point raised to the power of N divided by K times the concentration of A at the second data point raised to the power of N. All right, so all I did is take that rate expression and I stacked them on top of each other, right? One for one data point, one for the other data point. And there's a reason that I do this. What's going to happen to my expression, specifically if we looked at the right-hand side here? What can I do? I can cancel out those K's, right? I don't know what K is. So I can't have that floating around in my expression. If I knew what it was, great. That would make my life easy. But I don't know what it is. So that's why we're going to have this strategy of taking the ratio of these 2 data points, because that will cancel out that unknown value there from my expression. Get rid of it, because I don't know what it is. All right, now I can plug in my data from my data table here. Again, I just picked these 2 data points. I could have picked any 2. The rate of my first data point is that 0.015 divided by the rate of my second data point, 0.015, equals, now that K is canceled out, I can plug in my concentration data. Right, so using my data table here, plugging in those values into my expression, right, again, the whole trick was that I was going to take the ratio of 2 data points. All right, so first of all, just make sure that you could see. I took my data table. I picked 2 points. I used my rate expression, but I'm going to take the ratio of those 2 data points. So that's how I get here. All right, now, because both of these concentrations are raised to the power of n, I can kind of simplify this. Okay? And what I'm trying to solve for here is n, right? So algebraically, how do we get those exponents? What am I going to do to both sides? What is it? The log, right? So the magic of logarithms. If I take the log of both of these here, so I'm going to take the log of this side and the log of this side. First of all, I think we can do this without a calculator. What is 0.015 divided by 0.015? 1, right? So on the one side, I get the log of 1 is equal to the log of 0.1 divided by 0.2, or 1/2. What am I doing? All right, and this is 1/2 to the n. And in the magical world of logarithms, that n can be pulled out. All right, my exponent turns into multiplication. You can trust me and ask your algebra teacher for an explanation as to why that is. All right, but yes, my exponent of n, when I take my log, I can pull that out. So then how am I going to get n all by itself? Divide both sides by that log of 1/2, right? Move it to the other side. And again, just by looking at the data, what do we say n should be? 0. This is going to be a 0th order reaction because that rate doesn't change. And now everybody just take your calculator and convince yourselves that the log of 1 divided by the log of 1/2 is indeed 0. All right, so we can indeed get our value for n here. Correct. The log of 1 is 0. So that does it in and of itself. Yep. All right, so again, the trick here, we have this initial rate data, and the whole shtick is we're going to take the ratio of 2 of these data points. That's how we get our order. All right, so pretend like that's not there, and that I didn't give away the answer at the top. Y'all are going to take this data here and tell me what the order of this reaction is. Same strategy we did before. All right, so I'm going to take the ratio of two of these data points. I'm going to just arbitrarily pick. You get the same value no matter which two data points you pick. So my rate of my first data point divided by the rate of my second data point. Again, the whole shtick is by taking the ratio, k cancels out. So now I have 0.10 to the n. All right, so make sure that you can see how I filled in my expression here. Right, on the left-hand side, I have the ratio of those rates. And on the right-hand side, I plugged in the concentration of those two data points. Again, my goal is n, so I'm going to take the log of both sides. And by taking the log, I can pull out that n value. So then how do I solve for n? I'm just going to divide both sides by that log of 0.1 over 0.2. So what's my order? So this would be a second order reaction. All right, real quick. Now that I have my order, I can use this same data and actually solve for the rate constant k, right? Now that I have my order, I can pick one data point, 0.015 equals k times 0.10 squared, because I know my order, and that can allow me to solve for my rate constant k, right? So we can find both the order and our rate constant from this initial rate data. My voice was not ready for this. All right, I will see you all on Wednesday.